All right, thank you for the introduction. Hello, everyone. I'm very glad to be here showcasing my project. So my name is Yu. I'm from University of Michigan. This project is collaborating with my advisor, Professor Robert Dick. The project is called the GOODPUT system. It is essentially a machine learning driven optimization framework for dynamic spectrum control in heterogeneous wireless local area networks. So a very quick summary, like a one-sentence summary of what is the goal here. We're trying to optimize the GOODPUT in spectrum constraint scenarios, for example, university campuses, sports stadium, and also music concerts. The GOODPUT is defined as useful communication throughputs, so we're excluding protocol overheads, we're excluding packet retransmissions, and also network congestion overheads. So whatever it left for the application data being received by the end device is what we're being interested, measured, and optimized. So in order to achieve this optimal setup, we need to do three things. The first one is access point channel assignments, meaning we have to figure out the best slot to allocate our candidate channels for each access point. The second one is channel bounding decisions. So channel bounding is a concept in computer networks to allow us to merge multiple consecutive 20 megahertz channels into a wider channel to support higher throughputs. And last but not least is the wireless devices, sometimes also called stations, to AP mappings. We need to figure out the best destinations for each stations. So this is a very classic problem. Researchers and industry experts have been, try to do research to improve connectivities and also improve network speed for the past two decades, maybe. But why we're still interested in this problem in 2026 is because we're experiencing a huge amount of devices, and also we can see there's a very fast growing pattern in the past 2 decades. Reported in 2024, we're having around 9 billion of mobile devices, active mobile devices, and also have around 2 billion computers, PC and laptops combined. One important thing is more than 70% of the connected devices using 2.4 and 5 gigahertz bands make the existing one extremely congested. And also, they're now extending their connections to 6 gigahertz, which was introduced a couple years ago. The second key reason is the existing solutions remain suboptimal. The projects can be either categorized into access point-centric solutions, like load balancing, heuristic-based channel selection, and dynamic channel boundings. And also, or on the other side is station-centric solutions like AP selections, intelligent application, traffic controls. So the thing here is they're not collaborating both parties together, but in the real wireless environment, access points and stations, they're working together to do the communication. So part of our job here is to break the boundary and formulate both parties in one function to achieve even better performance. So our project is inspired by 2 observations. The first is we believe there's a supply and demand relationship in the wireless communication network. By analyzing the device communication traces, we're able to understand how much bandwidth does each connected station required. And also on the other side, if we understand the channel access point channel information, we're able to understand how much bandwidth does each access point can provide. So this supply and demand relationship tells us how to operate our network. The other observation is for OFDMA, which is the orthogonal frequency division multiple access, is a technology introduced in Wi-Fi 6. So what it does is dividing wireless channels in smaller subcarriers, also sometimes called resource units. So it can serve multiple users at the same time. So on the picture, the top picture, before OFDMA, each time slot, it can only deliver data to one destination. But for OFDMA, we can deliver packets into different destinations at the same time. So that makes us to believe that we can formulate this problem into a classic multiple knapsack problem. We can think of the access point as a knapsack with a capacity, and also each demands from the stations as a weight. So the goal for a multiple knapsack problem is to pack as much as possible weight without exceeding the capacity And same goal here in the wireless communication network. We're trying to satisfy as much as user and also guarantee their service without exceeding the supply that each access point can provide. So that helped us to build this straightforward three stages GOODPUT system. So we do have a network sensing stage, optimization stage, and also an underlying infrastructure control stage. By doing this pipeline, we can ideally achieve a optimal network deployment. So let's take a look one at a time. So the first is network sensing. The system do two things. So the first one is we use the internal Wi-Fi module to do a quick scanning on the 2.4 and 5 gigahertz bands. We want to see the channel distribution and try to figure out where is the best possible place to allocate our candidate channels. The second is the station demands. So instead of just using the history to figure out the demands that each station will require at the current timestamp, there's a LSTM, the long short-term memory neural network dedicated to tackle this problem. Is also compatible with most, Windows, Linux, most of the popular operating system, which is also very lightweight, to predict the short future demands that each station has. So by understanding those two sensed information, we can propagate those results into our optimization stage. So our optimization formulation is very similar to the multiple knapsack problem, also catering to this network scenarios. So it maximizes the total delivered data under some constraints. The first constraint is each access point use exact one configuration at a time. And also each station is associated with one access point at one time slot. And also the supply that access point can provide needs to be lower than the ideal capacity that we calculated. So the key takeaway here is by doing this calculation, we can have access point channel assignments. Second is channel bounding decisions, and also wireless channel to AP mappings. By having those three components, we can guide our system to achieve optimal setup. But before reaching to that state, there's an underlying infrastructure control stage we have to do. So we have to configure the access point to do what they should do, and also advise each stations to roam toward their appropriate destinations. To achieve that, on the access point site, we use Selenium WebDriver, which is the automation script that we can use to interact with routers' web-based AP control interfaces. Most of the off-the-shelf commercialized AP does have these interfaces that we can use Selenium to control with. On the other side, we have wireless devices. We use WPA CLI to advise devices to roam between APs in the same managed network. So as a result, we actually built our own hardware hardware testbed. So we do have 3 access points, 15 hardware hosts. We virtualized 100 stations. So we also compare with 3 baseline approaches: the RSSI, which is the most widely used nowadays. Like everybody is using RSSI connection in this room. And the second one is dynamic load balancing. That's AP side optimization, and also a deep neural network-based access point selection. That's the optimization deployed on the station side. So as a result, you can see on the left side of the figure, the orange line is representing the aggregated GOODPUT of the GOODPUT system throughout the entire 1-hour experiment. And we achieve a higher aggregated GOODPUT compared with all 3 baseline comparison. Number-wise, we did 2 sets of experiment. We're not expecting every station to follow the exact same protocol that we proposed. So we have a subset of the stations that follow what we proposed, and the other part is what we consider as legacy devices. So combining 2 parts together, we outperform RSSI for about 47.9% in aggregated GOODPUT, outperform access point selection by 19.3%, and also by outperform load balancing by 17.1%. So if we excluding those legacy devices, assuming every station is follow our network, we can achieve even higher performance gain. So another benefit that the GOODPUT system can provide is it can have a more optimal spectrum utilization utilization. So instead of having a fixed channel width, like other comparison baseline, at the same width, for example, 80 megahertz, the GOODPUT system is smart enough to understand what is the best possible combinations to guarantee reliable service and also reduce interference with other managed networks. So for example, in this 1 hour experiment, our GOODPUT system reduced down to 200 megahertz in total after 482 seconds. Typically, it reduced 14% less spectrum than the static baselines. And also, this benefit can significantly lower the interference in congested environments. And that's everything I have prepared for today. Thank you.